Let me introduce Professor Lin-Shan Li. He's been with the National Taiwan University since 1982. His early work focused on the broader area of spoken language systems, particularly focused on the Chinese language. Had a number of breakthroughs early on in that language. His more recent work has been focused on sort of the fundamentals of speech recognition and on network environment issues like information retrieval, semantic analysis of spoken content. He's an IEEE Fellow and an ISCA Fellow. He served on numerous boards and received a number of awards, including very recently the Meritorious Service Award for IEEE Signal Processing Society. So please help me welcome Professor Lin-Shan Li.
Hello, so you can hear me, right? Good afternoon, and thank you, Larry. It's my great pleasure today to be here presenting to you Spoken Content Retrieval, Lattices and Beyond. My name is Lin-Shan Li from National Taiwan University. In this talk, I'll first introduce the basic problem and some fundamentals. And then I'll spend more time explaining some recent research examples. I'll show you a demo before the conclusion. So first, introduce the problem. We are all very familiar with text content retrieval because it has been very successful. For any user queries or user instructions, usually we refer them as queries. The desired information can be attained very efficiently in real time, usually referred to as documents. All users like it, and it even produces very successful industry. Now, today, we all know that all roles of text can be accomplished by voice. On the content side, the spoken content, we do have spoken content or multimedia content with voice in audio part. On the query side, the voice query can be entered via handheld devices. So it's time for us to consider spoken content retrieval. Now, this is what we have today for everyone. When we enter text query, we get text content. Now, both the queries and content can be in form of voice in the future. First, we may use text queries to retrieve spoken content or multimedia content, including audio part. And for this case, very often authors refer them as spoken content, spoken document retrieval. And very often a small subset of that problem is referred to as spoken term detection. In other words, to detect the query term in the spoken content. Of course, we can also retrieve text content using voice queries. In that case, usually referred to by the authors as voice search. And however, in this part, because the document to be retrieved is in text form, and therefore will be out of the scope of this talk. So I'm not going to spend more time talking about voice search. Now, of course, we can do the other side. That is to retrieve spoken content using spoken queries. And sometimes the user referred to this as query by example. And so in this talk, I'll focus on retrieval of spoken content, primarily using text queries. But sometimes we can also consider the case of using spoken queries. Now, as we all understand, if the spoken content and spoken queries can be accurately recognized, then this problem will be reduced to the well-known text content retrieval. So there will be no problem. Of course, that never happened because we know there are serious recognition errors in most cases. So that's the major problem here. Now, today, we understand that there are many handheld devices with multimedia functionalities available today commercially. And also, there are unlimited quantities of multimedia content, which is fast growing over the internet. So we wish to be able to retrieve not only the text content, but as well the multimedia and spoken content. And in other words, the wireless and multimedia technologies today are creating an environment for spoken content retrieval. Let me repeat again that the network access is primarily text-based today, but almost all roles of text can be accomplished by voice. So let me mention very briefly some fundamentals. First, as we understand, the recognition always gives errors for various reasons. For example, spontaneous speech, for example, OOV words, or mismatched models, and so on. And that makes the problem difficult. So a good approach may be to consider lattices with multiple alternatives, rather than the one best output only. In this case, of course, we can have higher probability of including correct words, but also in that case, we have to include more noisy words that cause problem. But on the other hand, even if we have the lattice, we still have the problem that some correct words may not be included because they are OOV words and so on. On the other hand, when we use lattices, that implies we need huge memory and computation requirements. That's another major problem. Of course, there exist other approaches to solve the similar problems. For example, people use confusion matrix to model recognition errors and try to expand the query and document using confusion matrices. People also use pronunciation modeling to try to expand the query in that way. People also use, say, fuzzy matching. In other words, the matching between the query and the content does not have to be exact. These are all very good approaches. However, I won't have time to say more about this since I'll focus on lattices here in this talk. Now, the first question is, how can we index the lattices? Well, a lattice looks like this. And usually, the most popular approach to index a lattice is to transform the lattice into a sausage-like structure like this. In other words, a series of segments. And every segment includes a number of word hypotheses with posterior probabilities. In this way, the position information for the words can be readily available. In other words, say word 1 is on the first segment and word A is on the second segment. So word 1 after word can be followed by word A, and that is a bigram and so on. In this way, this is more compatible to existing text indexing techniques. Also, in this way, the required memory and computation can be reduced slightly. In addition, we may notice that in this way, we can add more possible paths. For example, word 3 cannot be followed by word A in the original lattice, but here this becomes possible. Also, the noisy words can be discriminated by posterior probabilities, because we do have scores here. In either cases, we notice that we can match the n-grams of this lattice with the query. For example, we have the bigram word 3 followed by word A. Then as long as this bigram exists in the query, that helps. So we can count all the possible n-grams and accumulate the scores and so on. Now, there are many approaches proposed for such kind of indexing of lattices. I just list a few examples here, and I think today the most popular ones may be the top two, the posterior position-specific posterior lattices, or PSPL, confusion networks, or CN. Also, another very popular one will be the weighted finite state transducer, WFST. Now, let me take 1 minute to explain the first two, the position-specific posterior lattices, PSPL, and confusion networks, CN. Suppose this is a lattice, and these are all the possible paths here, the word sequence. And the PSPL, or position-specific posterior lattice, try to locate every word in a segment based on the position of that word in a path. For example, word 10 here appears only as the fourth word in a path, so it appears in the fourth segment. On the other hand, CN, the confusion networks, try to cluster the words together in a cluster based on, for example, time spans and word pronunciation. So, for example, the word 2, word 5, word 10 may have very similar time span and pronunciation. They may be clustered together, and they may appear in the segment 4 here. So in this case, you may note that the different approach gives different indices. Now, a major problem here is OOV words. As you understand, the OOV word cannot be recognized, therefore never appear in the lattice. That's important because very often the query words, the query includes OOV words. However, if we look carefully, there are many approaches to handle this problem. I think the most fundamental approach is to use subword units. Let's take this example. Suppose a OOV word W is composed of these 4 subword units. Every small wi is a subword unit. For example, phoneme or a syllable or something. These are also subword units, and this is lattice, and these are arcs and the words here, because this W is not in the vocabulary, so it's not recognized here. However, if we look at carefully, we notice that the word is actually here. It is hidden at the subword level. So it can actually be matched at subword level without being recognized in the lattice. And that's a major approach that different ways can be developed to try to handle this using subword units. One example is to construct the same PSPL or CN based on subword units, for example. Now, there are many different subword units have been used in this approach, and usually we can categorize them into 2 classes. The first one is linguistically motivated units, for example, phonemes, syllable character, or morphemes, and so on. The other one is data-driven units. In other words, they are derived using some data-driven algorithms. And different algorithms may produce different names. For example, someone called it particle, someone called word fragments, or phone multigrams, or morphs, and so on. Of course, there are some other different approaches. If we do have the query in voice form available, in that case, we can also match the query in speech and the content in speech directly without doing recognition. In that case, we can avoid the recognition error problem, and we can even do it in a unsupervised way. In that case, we even don't need lattices, and this can be performed in, say, frame-based matching, for example, like DTW, or segment-based approach, just matching the segments, or model-based matching, and so on. However, this kind of approaches do not use recognition and therefore do not have lattices. So I won't spend more time using about these approaches. I'll just focus on those with lattices. Okay, so below with these fundamentals, I'll just describe to you some recent research examples. I have apologized that I can only cover a small number of examples. So many examples I just cannot cover. Below, I'll assume the retrieval will look something like this. This is spoken archive. After recognition, based on some acoustic models, we have lattices here. Now, the retrieval was applied on top of these lattices. Here, the search engine, indexing the lattices and search over the indices. And by retrieval model, I mean anything in additional. For example, confusion matrices, matching algorithm, or weighting, or learning, whatever. So I'll, based on this graph, to discuss the following. The first thing we can think about can do is to do integration and weighting. And for example, we can integrate different clues from recognition. from different recognition systems, from those based on different subway units, or including some other information and so on. In addition, a good idea may be to try to train those model parameters if we have some training data available. What kind of training data are needed here? Well, this kind of training data we need here are a set of queries and the associated relevant, irrelevant segments. For example, when user entered the query Q1, we get a list of here, and the first two are false or irrelevant, and the next two are true or relevant, and so on. We need a set of this kind of data. Well, such data does not necessarily to be annotated by person, by some people, because we can collect them from real click-through data. For example, if a user enter a query Q1 and he get this list, and then he skipped the first two items and directly click the next two, we may assume then the first two are irrelevant or false, and the next two are relevant. In this way, we can have click-through data. When we have this kind of data, then we can do something more. For example, we can use this training data to train the parameters here. For example, we train different weighting parameters to weight different recognition output, different subway units, or different information, including font confidence or font confusion matrix, and so on. Now here, let me show you very briefly two examples here. And the first one is that in this example, we actually use two different indexing approaches we just mentioned, confusion network and position-specific posterior lattices. In each case, we use not only the word-based indexing, but also those based on subway units. In each case, we accumulate 1 gram, bigram, 3 and trigram. And so we have a total of 18 different scores. And we try to add them together by some weighting to optimize some parameter describing the retrieval performance, which is called MAP. Here, by MAP, all the MAP I mentioned in this talk is mean average precision, which is the area integrated under this recall precision curve, and which is a performance measure frequently used for information retrieval. Of course, there are many other parameters, and I just have time to use one of them here. Now, we can try to optimize this parameter using some extended version of support vector machine. Now, here's the results. Here are the MAP results for the 18 different scores used individually. And this is the result when we integrate them together. You see we get about a net gain of about 7 to 8% of MAP, which is nice. Here is another example that we think it's possible to have context-dependent term weighting. In other words, the same term may have different weights depending on the context. For example, if the query is information theory, this information is very important. But if the query is speech information retrieval, then this word information is not so important because the important terms are speech and retrieval. In this way, different terms may have different weights in different contexts, and these weights can be trained. And here are the results. Using context-dependent weight, we actually get some gain on the MAP. Okay, these are some directly weighting. Now, what can we do next? Well, the first thing we think about is how about acoustic modeling? Can we do, just as we have so many experts in acoustic modeling, we can do discriminate training on acoustic models. So can we use this training data to re-estimate acoustic models? Well, in the past, all the retrieval are considered as on top of recognition output. They are two cascaded independent stages. And so retrieval performance really rely on the recognition accuracy. So why don't we consider these two stages together as a whole? Then the acoustic models can be re-estimated by optimizing the retrieval performance here. In this way, the acoustic models may be better matched to each respective data set. So in this way, we learn from the MPE and try to define a object function in these purposes. And here is the results. These are results for different sets of initial acoustic models. This is for speaker-independent models, and this for adapted by global MMR, and this by adapted further by a class MMR. And here, this MAP adapt is the adaptation by maximum A posterior probabilities. And these numbers are MAP, not the recognition accuracy. As you notice that we do have some improvements, but relatively limited. Probably because we were not able to define a good enough objective function. Another possible reason may be because different queries really have quite different characteristics. So when we put together many queries, and these different queries really interfere with each other in the training data. So we are thinking of why not use query-specific acoustic modeling. In other words, if we can re-estimate the acoustic model for every query, then that means this has to be done on real time, online. Is it possible? We think yes, because we can, based on the first several utterances, when the user clicks through and browsing the retrieval results, then all the utterances not yet browsed can be re-ranked by the acoustic model. That means the models actually can be updated and the lattice can be rescored very quickly. Why? Because we have only very limited number of training data, so the retrieval can be very fast. So this is the scenario that when the system gives the retrieval results here, and the user browse and click the first several utterances and indicating they are relevant or irrelevant, then these results are actually fit to the acoustic model to re-estimate the models. When we get new models, and these are used to rescore the lattice, and that is used to re-rank the rest of the utterances. So what is the results? Well, we can see just with one iteration of model re-estimation, which makes the real-time adaptation possible, and we do have some improvements here. Now, what else can we do? Well, how about acoustic features? Well, yes, we can do something on acoustic features. For example, if we know an utterance is known to be relevant or irrelevant, then other utterances similar to this one is more probable to be relevant and irrelevant. So in this case, we have the same scenario that when the user see the output and he click the first several utterances, and we can use the first several utterances as reference, and those not yet browsed are compared with those clicked based on the acoustic similarity and then re-ranked. And in this way, let's see whether it is better or not. And then we need to first define the similarity in acoustic features. We first define for a utterance, the hypothesized region is the segment of feature vector sequences corresponding to this lattice, this utterance and this lattice, corresponding to the query queue in the lattice with the highest score. For example, for this utterance of feature vector sequence, and this is the corresponding arc for the query, and this is the hypothesis region. Now, similar, there's another utterance with a sequence here and hypothesis region here. Then the similarity can be derived based on the DTW distance between these two regions. And in this way, we can perform the scenario we just mentioned. And here are the results, again, for the three sets of acoustic models. And we may notice that in this way, using acoustic similarities, we get slightly better improvements as compared to directly re-estimated acoustic models. Okay, so what else can we do? Well, we may consider a different approach. That in the above, we always assume we need to rely on the users. That gives us some feedback information. Do we really need to rely on the users? No, because we can always derive relevance information automatically. We can assume the top n utterances on the first pass retrieval results are relevant or actually pseudo-relevant. And this is referred to as pseudo-relevance feedback. And here you see scenario. When the user enters a query and the system gives the first pass retrieval results, and these results will not be shown to the user, but instead we just assume the top n utterances are relevant, and all the rest are compared with this top n and see whether they are similar or not. And based on the similarity, we re-rank the results. And only these re-ranked results are shown to the user. And now we need to, okay, here is the results. You can see that with this pseudo-relevant feedback for different acoustic models, and we really have slightly better improvements here. Now, what else can we do? Well, we can further improve the above pseudo-relevant feedback approaches. For example, we can use graph-based approach. Remember above that when we, in the pseudo-relevant feedback approach, we assume the top n utterances are taken as references. We assume they are relevant. But in this way, of course, they are not reliable. So why don't we simply consider all the first pass retrieve results globally using a graph? In other words, we construct a graph for all utterances in the first pass retrieve results. And all the utterances are taken as, represented as a node. And then the edge weights are actually the acoustic similarities between the utterances. Now we may assume that the utterances strongly connect to utterances with high scores, or very similar to utterances with high scores, should have higher score. For example, if here X2, X3 have high score, then X1 should be higher. Similarly, if X2, X3 have low score, then X1 should have low score. In that case, the scores can propagate on the graph and then smoothed among strongly connected nodes. In this way, all the scores can be corrected. So we can then re-rank all the utterances in the first pass retrieval results using these corrected scores. And here is the results. And again, for 3 sets of acoustic models. And you may notice that now graph-based approach did provide higher MAP results in all cases. This is reasonable because this graph-based approach really considered globally all the first pass retrieval results rather than reference on the top n utterances only. Okay, what else can we do? Well, machine learning, of course. Machine learning has been used and shown useful in some work. So let me show one example of use of support vector machine in the scenario of, we just mentioned, the pseudo-relevant feedback. And here is the scenario. Again, when the user enters a query queue, here, and this is the first pass retrieval results. This is not shown to the user, but instead, we simply take the first pass retrieval results. We consider that the top n utterances are assumed to be relevant and taken as positive examples. The bottom n are assumed irrelevant and taken as negative examples. And then we simply extract some feature vectors from them, and then we try to train a support vector machine. Now, for all the rest of utterances, we simply, again, we extract the feature parameters and then re-ranked by the support vector machine. And then only the re-ranked results are shown to the user. So in this case, please know that then we need to train n SVM for every query online. Is it possible? Yes, because we only have a limited number of training data, so that can be very fast. Now, the first thing we need to do is we need to define how to extract the feature parameters to be used in training the SVM, where again we can use the, we just mentioned the hypothesis region. And suppose this is an utterance, and this is the corresponding lattice, and here is a query, and so this is a hypothesis region. We can divide this region into HM states. This HM state, and those feature vectors in one state can be averaged into one vector, and then these vectors for different states can be concatenated into a super vector, and that's a feature vector for this utterance. In that way, what's the results? Again, we can see the results for different acoustic models. You may notice that now this SVM is much better than graph-based, which is much better than the previous results. And again, of course, I have to mention that all results reported here are very preliminary. They are just obtained in preliminary results, experiments. Now, what else can we do? Well, all the above discussions are primarily considering acoustic models and acoustic features. How about linguistic information? Yes. For example, the most straightforward information from linguistics we can use is a context dependency, context consistency. In other words, the same term usually have very similar context, while quite different context usually implies the terms are quite different. So, what can we do? We can do exactly the same as we did using the SVM, except now the feature vectors represent context information. So we use exactly the same scenario that for the first pair retrieval results, we use top and bottom end to train SVM, except now we use different feature vectors here. Suppose this is an utterance and the corresponding lattices, and here are the query here, and we can construct a left context vector whose dimensionality is the lexicon size, and only those words appear to the left context have their posterior probabilities as the score. All the other words has 0 there. Similarly, we can have right context vector and the whole segment context, and then we can concatenate them together into a feature vector. And this has dimensionality of 3 times the lexicon size, 3 times of the lexicon size. Now, we can use this to do the experiments, and here are the results. Again, for 3 sets of acoustic models, and you may notice the context information really helps. So, what else can we do? Well, certainly concept matching. In other words, we wish to match the concept rather than literally. In other words, when we wish the system can return utterances or documents semantically related to the query, but not necessarily include the query. For example, if the query is White House of United States, and if an utterance includes President Obama, but not White House, not US, we wish it can be returned as well. Well, there are many approaches have been proposed for this direction. For example, we can cluster the documents into sets, so we know which sets of documents are talking about the same concept. We can use web data to expand the query or expand the documents. We can also use using latent topic models. But I'll show you just one example of latent topic approach. Well, this is very straightforward, and we just use the very popular, well-used probabilistic latent semantic analysis, or PLSA, in which we simply assume a set of latent topics between a set of terms and a set of documents. And the relationship can be modeled by probabilistic models trained with EM algorithm. Of course, there are many other approaches, and I don't have time to mention them. And here is the example work we did for the spoken archive. And we transformed into lattices. Then for any given query, we simply use the PLSA model we just mentioned based on the latent topics to estimate the distance between the query and the lattices, and that gives the results. Here are some preliminary results. These results are in terms of recall precision curve. And these three lower curves are the baseline of literal matching, simply matching the words. And the lowest one is on one best results, and the two upper ones are based on the lattices. Now, the three curves here are concept matching using the PLSA I just mentioned. As you can see, concept matching certainly is much better. So what else can we do? Well, user content interaction is certainly important. We know that user content interaction is important even for text content. In other words, when we retrieve text content, very often we also need a few iterations to get the desired information. Now, for spoken content, this is much more difficult because spoken content are not easily summarized on screen. They are just signals. So it's difficult for the user to browse, to scan, and to select them. So when the system gives a whole bunch of retrieval results, we cannot listen to every one of them and then decide which one we like. So that's a problem. What we propose is first we can try to select automatically key terms and construct title summaries to help browsing. And then we try to do some semantic structuring to help the user interface. And then we can try to have some dialogue to help the interaction between the user and the system. So below, I'll very briefly go through some of this. For example, key term extraction, which is very helpful in labeling the retrieved results and for the user to browse it. The key terms include two types at least, keywords and key phrases. Key phrase include several keywords, several words together. So for key phrase, we need to detect the boundary. And there are many approaches to do this. Here's one example. Suppose hidden mark model is a key phrase. Why? Well, you can easily find that hidden is always followed by the same word Markov. Markov is always followed by the same word. Hidden Markov is always followed by the same word model. However, hidden Markov model is followed by many different words. And that means this is the boundary of the phrase. In this way, the boundary can be detected by context statistics. Now, with the key term candidate, either it's a word or phrase, then we can extract many features to identify whether they are key terms or not. For example, prosodic features. Because very often the key terms are produced with longer duration, wider pitch range, and higher energy. We can also use semantic features, for example, from PLSA, because key terms are usually focused on smaller number of topics. For example, this is a distribution of the topic probabilities obtained from PLSA given a term. Now, this one looks like a key term because it is focused on only smaller number of topics. The horizontal axis are topics. And this one doesn't like a key term because it's uniformly used in many different key terms, in many different topics. Of course, lexicon features are very important. That includes term frequency and inverse document frequency, part of speech tags, and so on. Here is a result of extraction key terms using different sets of features. Here, the prosodic, lexical, and semantic features are here, and you notice that each single set of features are useful. However, when we integrate them together, we get the highest results. Now, for summarization, well, a lot of people in this room are doing summarization, so I'll just go through that very quickly. Let's suppose this is a document, includes many utterances, and we try to recognize them into words. Every circle is a word, either recognized correctly or incorrectly. What we do is try to select a small number of utterances which are most representative and avoid the redundancy. And they are used to form a summary. And this is the so-called extractive summarization. We can even replace this utterance with the original voice. So there is no recognition errors in the results. And I just show one example here. because we are selecting the most representative utterances. So it's reasonable to consider that the utterances topically similar to the representative utterances should also be considered as representative. So we can do similar on the graph-based analysis. In other words, every utterance represents as a node on the graph. And then we let the scores for representativeness propagate on the graph. In this way, we can get better scores and select better utterances and so on. These are some results. Let me skip this. Title generation. Titles are very often useful for if we construct titles for retrieve the document segments. It's useful for the browsing and selection of utterances. But title has to be very short, but readable and telling what it is. Here's one approach. We perform Viterbi algorithm over the summary based on the scores obtained by 3 models to select the term, to order the term, and to decide the length of the title. And in this way, we can have some good titles. Semantic structuring. There can be different ways to do semantic structuring, and we don't know what's the good approach. Here, just show you one example. And we can cluster the retrieved results into some kind of tree structure based on the semantic information, for example, latent topics. And in this way, every cluster can be labeled by a set of key terms. So that set of key terms indicating what they are talking about. And every cluster can be further extended into the next layer and so on. Here is another example, key term graph. In other words, every retrieved spoken document or segment can be labeled by a set of key terms. And then the relationship between the key terms can be constructed, represented as a graph. So we know what kind of information they are about. Okay, now finally, the dialogue. If we have all this, including semantic structuring or key terms summaries here on the system, and the user is here providing some query, so what can we do to offer them to have a better interaction? A dialogue may be possible, and many people here in this room are very experienced in doing something on spoken dialogue, so we wish to learn something from that. For example, we may model this process as a Markov decision process, or MDP. And in this way, what we can do is to, for example, we need to define some goals. The goals may be higher text success rate, except here the success indicates the user information need is satisfied. We can also define the goal to be a small number of dialogue turns, but here is small number of query terms entered. And in this way, we can define a reward function or something similar, and then maximize the reward function with similar users. And here is one example application scenario for retrieving broadcast news. And here, in every step, when user enter a query, the system returns not only the retrieved results, but also a list of key terms for the user to select. If the user is not satisfied with the result here, then he can look through the key term list from the top and select the first relevant to his need. And this key term list can be ranked by MDP. And here are some results. Let me skip this. So above, I have mentioned something about the key term, about summary title and semantic structuring and dialogue. So that's the something about the user content interaction. Of course, there are a lot more work needed before we can do something, really. Okay, now let me have a few minutes to show you a demo. And this is a course lecture. Oh, okay, let me go back to the slides first. This on course lectures. And As we know, there are many course lectures available over the internet. However, it takes very long for a user to learn to listen to a complete course, for example, 45 minutes. And therefore, it's not easy for engineers or industry leaders to learn new knowledge via the course lectures. And we wish to help. So we also understand there are lecture browsers available over the internet. However, we have to bear in mind that the knowledge in courses lectures are usually structured, one concept following the other. So the retrieved lecture segment possibly being very not easy to understand for the learner without enough background knowledge. And also, given the retrieved segment, there is no information for the learner regarding what should be learned next. So the proposed approach is to try to structure the course lectures by slides and key terms. We derive the course lectures by slides and derive the core content for the slides by key terms, and then construct key term graph to represent a semantic relationship among the slides. And also, all slides are given its length, timing information in the course, summary key terms, and related key terms and related slides based on the key term graph. And all retrieved spoken segments include all above information for the slides they belong to. And this is a system for a course on digital speech processing offered by myself in Taiwan University. So therefore, it is given in Mandarin Chinese. However, all the terminologies are produced directly in English. So this is a co-mixed data. Okay, so now let me go to the system. And this is the course, and the system actually we give a name of NTU Virtual Instructor. And it was recorded in year 2006, the total length 45 hours. Now suppose I heard something in the lecture about backward algorithm, but I don't know what that is. So I try to retrieve it. However, because I don't know it, so I may guess it is black word algorithm. So I just enter black word algorithm and then do the search. Here I'm searching through the internet and on the server in Taiwan University. So I rely on the internet here. And we see that here I'm retrieving the voice rather than the words. So the query word is black word algorithm, which are totally wrong. But here what we retrieve, a total of 56 results in the course. And here, for example, in this result, the first one is utterance of 8 seconds long. It is in these slides. It's slide number 12 of chapter 4. The title of that slide is Basic Problem 3 for HMM. And here is the, and this slide is labeled by these key terms, backward algorithm. Now I know this is the backward algorithm rather than the backward algorithm, and also Bang-Welch or forward algorithm, and so on. And note that because these utterances are represented in terms of lattices of subunits, so the subunit sequence of this backward algorithm is very similar to this one, and that's why I can retrieve it. And there are many of them, so if I go through them. Now, if I think I like to listen to this, so I can click here to go to that slide. This is slide number 12 of chapter 4. And slides here, the title is, this is done by myself, so this is a human-generated title. I don't need automatic generated title because every slide has a title, and the title is Basic Problem 3 for HMM. And here says this slide has a total length of 22 minutes and 57 seconds. So if I like to listen to this, I need to have 22 minutes. And in addition, this is the span of these slides in chapter 4 out of the 22 slides totally, and so on. And very important here is the key terms. Only those terms on the top in yellow are the key terms used in these slides. And those below here are relay key terms provided by the key term graph. In other words, the key term graph is quite complicated, not easy to show here. So instead, I just list the highly related key terms here below every key term. So for example, when I go through here, I saw there is a key term called a backward algorithm, another called forward algorithm, and backward algorithm actually relate to forward algorithm, and so on. Now, if I don't understand this one, so I like to know a little more. If I understand this, can I listen to these slides? So I click here. That gives me that this key term of backward algorithm actually first appeared in another slides, which appears earlier. And now you are in this slides, which is later. So probably there is no explanation about this. And if you really don't know about backward algorithm, you should go there. So I can click this one, and then I go to that slides, where it's like, okay, yeah, that's the other slides. And that is the first time that backward algorithm was mentioned. And that's that slides. And that's that algorithm here, that the key term in that slides. For example, in that slide, we also really have backward algorithm and forward algorithm. The forward algorithm is actually related to backward algorithm, and backward algorithm related to this forward algorithm, and so on. Now, let me show you a second example. Suppose I like to enter another query, which is frequencies. Now, I do the search. Now, in this course, there are a total of 64 results for the frequencies. Here, the first utterance of 6 seconds long appears in this slides of filter bank processing, labeled by these key terms. And the second is on pre-emphasis, and so on. If I'm interested in this one, I can click here to go to this slides. This is the slides on pre-emphasis. And I notice there is a summary of 15 seconds. So I like to listen to this summary. So, okay, I'm retrieving the summary from the type.
因此，越高频的部分越微弱，越不清楚。好，那我们就把它拉高一点啊。那么让我们的比较 sensitive 的感觉能够在这里能够感觉得出来。那这个就是我们这边所说的这个 pre-emphasis， 它在高频拉高的啊这个基本的一个说法。那
Okay, this is the 15-second summary. It's in Mandarin Chinese, I'm sorry, but I tried. The English subtitle is actually done manually in order to show you what was said in that summary. And okay, so this is the end of the demo. So let me come back to the PowerPoint. So in conclusion, I usually divide the spoken language processing over internet into 3 parts: user interface, content analysis, including such as key term extraction or summarization or so on, and the user content interaction. We noticed that user interface has been very successful, however, not very easy usually, because users usually expect the technology to replace human beings. For content analysis and user content interaction, which are not easy either, however, because the technology can handle massive quantities of content, while human being cannot, so the technology does have some advantages. Now, the spoken content retrieval is the one which integrates user interface with content analysis and user content interaction, therefore maybe offer some interesting, attractive applications in the future. So eventually, I'd like to say that I think this area is only in its infant stage, and there's still plenty of space to be developed and plenty of opportunities to be investigated in the future. And I noticed that many groups have been doing some work in this area, and actually many people in this room have done some work in this area. So I wish we can have more discussions and more work in the future, and hopefully we can have something better, much better than what we have today in the future. Just as in speech recognition, we are now having much better work than several years ago. So we wish we can do something more. Okay, this concludes my presentation. Thank you very much for your attention.
Lin Shen, thank you very much for a very interesting talk. One question I have for you is that a lot of people in the audience are working on a related, somewhat related problem, which is voice search. And one of the issues that come up in voice search is sometimes you say something, it gets the speech recognition wrong, and then you repeat the query to get it right, although the sets of choices it may come up with may be sort of similar and overlapping. It would seem to me that that has some relation to relevance feedback, in the sense that the user is sort of giving an additional set of information about the previous query that was dictated. And I'm just wondering if you and the people you work with have ever looked into this sort of problem, or whether you have any opinions on whether you could get improvements by looking at somehow taking the union of multiple queries in a voice search sort of task to try and improve results using similar methods to what you talked about in your talk.
Thank you very much. I think certainly it's a very good idea, and actually, as I mentioned in the beginning, in this talk, we are not talking about voice search. But in your experience, for example, when the repeated queries may provide some good information or correlation about the intent of the user, certainly that's very helpful. For example, in what I mentioned, the dialogues, we actually allow the user to enter the second query and so on. And that gives actually the interaction or the correlation between the first and second queries and so on. I think that's the only thing we have done up to this moment. But I think probably what you said implies much more we can do. And I think as I mentioned, we just have too much work to be done. And so we can think about how to implement what you think about in the future, yes.
Thank you very much, Professor Lee, for a very interesting talk. I have a detailed technical question on your SVM slide.
Okay.
So if you can go back.
Okay, for
the SVM, that you take the positive examples and the negative. Oh, okay, this slide.
Yes.
So my question is, when you train your SVM, it seems like you're only taking the high confidence examples for positive and negative examples. So in the margin, you're pulling the examples from very far from the margin. And in the testing stage, if you have some difficult examples that are very close to the hyperplane, then you might probably have a very hard time doing the...
Yes, certainly you are correct. But, well, that's all we can do at this moment, because you know nothing about these results, right? You just have the first pass results here, and all we can do is to assume the top and bottom, and then construct the SVM. Of course, in the middle, close to the boundary, is a problem. However, SVM already provides some solution, for example, the large margin concept. So they try to provide some help on those margin, and also there are some allowance, right? So we just try to borrow the idea from SVM and try to see if we can do something better.
Okay, thank you.
Thank you.
I have a question.
Sure.
Thank you. Great talk. There's a lot of parallels with methods developed, and this is really extending what Michael was saying, with text-based web search with this problem, even beyond voice search. Some methods I think that have been developed by this community that would probably benefit the web search community, and vice versa. And I wanted to ask you to comment on that and your awareness of the literature there and opportunities for this cross-fertilization. In web search, the query writing is well established, and also in the click feedback web search, they found a lot of benefits from distinguishing between clicks from users and good clicks, because clicks tend to be noisy. And so there's been a lot of work in the web search community about modeling clicks and, determine good clicks and use those, weight those more heavily for feedback. And also just basic things like editorial relevance feedback by, bunches, large groups of users to determine the relevance and use that as feedback as well. So I just wanted to ask you what your thoughts are on this opportunities for cross-fertilization between these two areas.
Yeah, sure. There are a lot of possibility to learn from the experience in voice search to do on this part of work. We just don't have enough time to explore the possibilities. As you mentioned, this click may be divided into several categories, and they can be learned or something like that. And I think that should be what to be done in the future. But on the other hand, we also learn a lot from other areas such as text retrieval. And then, for example, the relevant feedback or pseudo-relevant feedback or learning to rank or something. Much of some ideas are borrowed from their community. So certainly cross-area interaction is very helpful because this area is actually interdisciplinary. On the other hand, we really try to do something more, we are more familiar in speech area. For example, acoustic modeling. For example, the acoustic features and so on. And we try to, for example, spoken dialogue. And we try to borrow all those good ideas and good experiences in speech and see if that can be used in content retrieval. And I think we just have, as I mentioned, we just have plenty of space to be explored in the future. Thank you very much. Thank you very much.